from Valparaiso University. She will talk about Einstein-Gauss-Bonnet supergravity and black holes with unbroken supersymmetries. Please go on, Olivera.
Thank you, Ruggero, and thank to everybody for coming here, wherever we are. I mean, because it is nice really at least to see your names written in the list. So I hope that you will not be disappointed. With this talk, I'm coming back to the subject of supergravity. This is, it has been done in collaboration with Laura Andrianopoli and Gaston Giribet and the student from Chile, Dario Lopez. And unlike the talks that I had opportunity to listen recently and that were like reviews of many papers and many works, I'm going to present something that we started working just in less than 2 years ago. But the subject is again not a standard supergravity, so but kind of I would say unconventional, but not in Jorge Zanelli's style of unconventional supergravity. So in fact, this work was not easy, and we could not use many results known from standard supergravity, and somehow we had to start from the scratch, understanding this theory. So that's why, in fact, I'm going to talk slowly, and please, I would like to invite everybody to, just a moment, because page does not, I don't know how to, I think it is stuck. It does not, I cannot turn pages. Just a moment. Maybe I will just, I don't know why I cannot, maybe I will have to use,
there is only one page. There is only one page in this PDF.
Yes, oh, I'm ridiculous. I open a wrong file just with the title.
No.
Okay, yes, okay, so here is the right one. Well, do you see it now? Ah,
yeah.
Yes.
Sorry, going to the beginning. Ah, I don't want to. Wow. Okay, perfect.
Perfect.
Yes, now we are back and now it works. Okay, so as I told, I would really like to invite everybody to interrupt me during the talk, because it is a kind of boring talking 1 hour without feedback. So I hope that you will ask me questions. So my plan is extra simple. First, I will tell you why I'm working with Transsignments supergravity. After that, I will show you kind of interesting solutions, because Transsignments supergravity has this feature that it incorporates matter like gauge fields. So this black hole will be hairy, even though we start directly from supergravity theory without coupling standard matter. And after that, we will study physical properties of these solutions. Of course, there are really like 3 pages of discussion and open questions, because there are still many unknown things that we have to investigate. Okay, so the idea, I will start with long introduction, and I apologize to everybody who is an expert in Transsignments supergravity, because in Transsignments theory, because I saw in the talks and in participants that they're experts on that. But I also know that there are other participants that are not so used to Transsignments supergravity and Transsignments theory. So I want to tell you how you can think that you work with usual gravity and find yourself suddenly in Transsignments gravity without realizing that. Just imagine that for any reason, we know that there are many reasons that you want to study higher curvature terms or in the framework of ADS-CFT, or just to see corrections to general relativity. So whatever is the reason, let's start, you take like the simplest case, that means 5-dimensional gravity, because in 4 dimensions, we know that general relativity of Einstein is the only one that has second derivatives of the second order in the metric. So you start from 5 dimensions and you choose just first correction, that is quadratic correction of the type of Gauss-Bonnet. And it is characterized by a coupling constant, and we also have a cosmological constant because we are interested in asymptotically anti-de Sitter spaces. So as it is well known, we can write equations of motion of Gauss-Bonnet, but they can be factorized in an interesting way, where it is clearly seen that, of course, if coupling constants allow so that it can have 2 particular solutions, that is pure global anti-de Sitter in the sense of maximally symmetric space-time. And one will have one radius, another will have another radius, and in general, this radii now depend on the Gauss-Bonnet coupling. So this is, in this case, we can always linearize this theory around ADS background if the vacua are different. And in this sense, Einstein-Gauss-Bonnet contains sector that is just, that can be seen like a small correction or big if you want, but at least small correction is allowed with respect to general relativity. However, what happens if you take now that 2 radii are the same? I will call them L. So this bare anti-de Sitter radius is rescaled. So this is my new anti-de Sitter radius. In that case, there will be 2 anti-de Sitter vacua with the same radius. And this is possible only for very particular Gauss-Bonnet coupling. So the point is that if by some reason you choose a Gauss-Bonnet coupling in this way, you can finish with Transsignments gravity in 5 dimensions. And this is problematic for the following, because this limit is not continuous, because Transsignments theory is completely different than Einstein-Gauss-Bonnet. In that sense, my title was a bit misleading, making you believe that I will talk about Einstein-Gauss-Bonnet, but in fact, this is Transsignments theory. So the easiest way how you can see that this theory is completely different is just looking static black hole solutions. To make the difference more dramatic, I wrote a theory static solution in d dimensions, the same action, Einstein-Gauss-Bonnet, and I assume that vacua, of course, it is not just Einstein-Gauss-Bonnet, but in general, I can add other nonlinear terms in such a way that I can have k-fold degenerate vacuum, not only twice like in Gauss-Bonnet. So as you can see, when k is different than 1, we don't have Schwarzschild-like asymptotic behavior. So even in the simplest case of static black holes, fall off is slower. It tends to the anti-de Sitter space in a much slower way. And in completely particular case, when dimension is exactly 2k plus 1, then this asymptotic behavior is the most dramatic. And then, in fact, it does not tend to 0 mass term, but it becomes constant. And these are called dimensionally continued black holes. I will review them later. But the point is that these dimensionally continued black hole, they look exactly the same as BTZ black hole in 3 dimensions that are solutions of general relativity. So this kind of theory, so now it is interesting question. First, how much these 2 solutions are similar, whether it is just by expression or there is something deeper. And also the idea is now to understand a bit better Transsignments gravity and maybe some more interesting solution than just dimensionally continued black hole. So conclusion is just that Gauss-Bonnet term with this particular Transsignments coupling is not just a correction, that it drastically changes. So let's now, how to see the best this change. Let's now, from now until the end of the talk, I will take exactly this coupling, and I will move to first order formalism, because this formalism will show the nicest properties of the Transsignments gravity. So I will allow that field bind and spin connection are two independent fields. Of course, I need it also for supergravity, because we know that fermions are source of the torsion, and that's why we need them. And we, of course, define curvature to form and torsion to form. So using this formalism, we can just rewrite original Gauss-Bonnet action, and it becomes Transsignments anti-de Sitter gravity that has this form. So, so this is just rewriting. You can see that we have only one coupling constant related to anti-de Sitter radius, and gravitational constant, of course, that multiplies the action. Now let me summarize. At first sight, it looked just like rewritten action, but in fact, this action has deep differences with respect to anti-de Sitter gravity. First, it can have a torsion different than 0 on shell. It is not any longer the only solution of equations of motion. It allows non-trivial torsion. And what is the most remarking is that it has more local symmetries than just general relativity, because instead of having just local Lorentz symmetry, now it has local anti-de Sitter symmetry, in the sense that there is also gauge field along ADS translations. So because we have more symmetries, it means that we have different number of degrees of freedom, because each symmetry is, of course, is related to redundant fields. So it turned out that, in fact, when we include all torsion and metric, contortion and metric degrees of freedom, in total, Transsignments gravity in any Transsignments theory has much more degrees of freedom than just Einstein-Hilbert. See, and even more interestingly, depending on initial conditions, we can finish in different sectors of phase space of this theory, where each sector has a different number of degrees of freedom. So, in 3 dimensions, Transsignments gravity does not have degrees of freedom. It is the same as general relativity, but in general, in higher dimensions, Transsignments gravity has degrees of freedom, propagating in the bulk. However, because if we choose special initial conditions, we can anyway finish in topological sector of Transsignments gravity. So each Transsignments gravity has topological and non-topological sectors. That's why it is very difficult to apply any formula. For example, if we find some solution, we cannot just apply any formula to calculate charges and other properties, because we don't know in which sectors we are, because we can have different formulas depending on different sectors.
Sorry, Olivera, we have
Yes.
a question by Peter.
Of course, Peter. Hi.
No, do you have the gravity photon here, or?
Okay, I have a field associated to U1 symmetry, but the action is not. I will write later the action, but it is not Maxwell field, so it is not graviphoton in the sense of standard supergravity. It is U1 field that also can have some charge, but it is given by Transsignments U1 action.
Thanks.
There is also another question by Cristobal Corral.
Cristobal.
Hi, Olivera. Does Transsignments gravity has a well-posed Cauchy problem? in this sense?
Honestly, I don't know, but I guess, do you know why? The point is that you have to define that there are different sectors. You have to pose Cauchy problem in different sectors. So what I was, when we were looking conditions, when we were solving equations here, in fact, we discarded, we didn't formally check Cauchy problem, but we discarded the solutions where initial conditions don't determine evolution of the system uniquely. So that's why I think that in the sector that we chose, that in the sectors there is more than one, that we have well-defined Cauchy problem, but maybe in some other sectors you can have a bad defined problem. It has to be checked formally.
Okay, thank you.
Okay, so just now before I jump to supergravity, just to repeat that now we have more local symmetries. We have gauge theory for anti-de Sitter group, or better to say SO2-4 group, and this is algebra of SO2-4 group. And beautiful thing is that now our field binding and spin connection, they're just component along gauge generators. So we can define the field strength and define completely standard gauge theory starting from this gauge field, where you can notice that global anti-de Sitter space corresponds to pure gauge. If you have torsion and global anti-de Sitter space, then F is 0. So it has 0 locally propagating degrees of freedom, but we saw that we cannot linearize theory around that background. So this is non-perturbative. Also, as many know, now when we have a gauge field, if we rewrite our Einstein-Gauss-Bonnet action with this coupling in terms of this gauge field, in fact, we discover that our action is Transsignments action. That means that Lagrangian, in fact, is a Transsignments form. That means that if we define this invariant F3 cubic invariant, if we define it locally, it can always be written like exterior derivative of some Transsignments form, but globally not necessarily. So we can expect some interesting global properties of this action, as we will also find that they exist. And notice now what is interesting. For our action, we have a symmetric invariant tensor that here defines the trace between the generators that is given like Levi-Civita, that it exists in any odd dimension. So we have a Transsignments action in any odd dimension. However, if we introduce some other group, some supersymmetric extension of anti-de Sitter group, and also if we define symmetric invariant tensor for that, we can obtain a different kind of Transsignments supergravities. In fact, Transsignments not only supergravities, but Transsignments gravities and theories. So exactly this is the idea to introduce Transsignments supergravity. We extend, this is in fact done, I didn't cite the paper, Troncoso, Zanelli. I mean, maybe I cited later. I was a bit sloppy with references, but in the paper you have all the references. So we take now anti-de Sitter group and we extend it to super anti-de Sitter, that is in fact SU22N, and bosonic sector of these fields has additional SUN non-abelian field that is internal symmetry. And also there is this, it is necessary to have also this U1 field. This is what Peter asked. Super algebra allows addition. This is the maximum supergroup that we can have. Bosonic sector and of course fermionic sector, where as Jorge Zanelli mentioned in his first talk, this kind of supergravities not necessarily have the same number of bosons and fermions. If you just look at the dimension of the algebra, of course, there are some ends where they can coincide just by chance. And this, if we see algebra, for example, we see that this U1 group, I call it U1Q because here we can have other U1 subgroups, and we will have. So just to distinguish, this U1 group really makes fermions charge, but only when n is different than 4.
Sorry, Olivera, we have a question.
Yes.
Hi, Olivera. It's Omar
Hi.
here.
Hi, Omar.
You said something about that in this Transsignments coupling, you can make perturbations around the ADS backward, right?
No, I told that you cannot make.
You cannot, okay.
Yes, because you have like you have F squared, where F is, if F is global ADS, then it is 0. So you cannot make only about if you choose this K-fold, two-fold degenerate anti-de Sitter background, because linear approximation gives you 0. I mean, it does not, there is no linear term. So you can.
This is a like common feature of Transsignments gravity. I mean, in any dimensions, it will be the same, right?
Yes, if you take global anti-de Sitter, you don't have a linear term. You cannot linearize equations of motion. But if you add, and in fact we did it with Zanelli and Troncoso in I think 2006. I mean, we had global ADS, but we added some non-abelian matter, SUN, SU4 in particular, and then we managed to have a well-defined sector that has a linear approximation. So it depends, and again, from the sector.
Thank you.
Okay, so let me, because in general, I will take n equal 4 because I'm interested when we were working, in fact, we were interested in finding BPS solutions. So, and I will tell you why when I review dimensionally continuing black holes. Namely, in general, this black hole can have lower energy. When you take the smallest black hole, it can decay in a naked singularity in general because it has smaller energy. So we wanted to see if we find BPS states, maybe supersymmetry will prevent this black hole to decay and keep it stable. And in fact, it was done also just in the case of without non-abelian fields. It is shown that it is possible to get BPS states of dimensionally continued black hole by Camphora and Troncoso, I think, and other authors. But we wanted to have also some matter. You will see that really SUN fields play the role of the matter. So we chose n equal 4, first of all, because SU4 is isomorphic with SO24. So it shows somehow like a first guess to construct something that will provide balance between gravitational forces and internal forces. This was our motivation. But finally, we saw that relevant group was not so much SU4, but SU2. So it could, in general, probably be done for other n. But n equal 4 has special feature is that these fermions decouple. They don't decouple completely, but at least they give neutral fermions, but they couple to gravity. So through this coupling, they will introduce non-trivial effect. And this is funny when we find solution. In fact, here kinetic term will disappear for U1 field, and it will be locally pure gauge. But globally, it will give some topological charge that will also contribute to stability of our solution. So it is really interesting, the role of this U1 Q field. Okay, So just before I start now to more concrete things, let me summarize that I use n equal 4 supergravity. When fermions become neutral, U1 Q field will just become a number. That means it becomes central extension in the algebra. Kinetic terms disappears. Okay, in this case, okay, I repeat again, our fields are gravitational field. I use calligraphic letters for non-abelian internal symmetry. There are fermions, Dirac fermions, and also U1 gauge field that finally, I mean, I keep it, but finally everything will be neutral. I won't keep much, I'm just writing bosonic action because in one talk I eliminated it. So I misled the audience thinking that they have Maxwell field and standard actions, but no, here all interaction and kinetic terms are determined by Transsignments action. So SUN field is Transsignments. Okay, Lagrange gravitational part of gravitational part, you know, but also this is a kind of a Gauss-Bonnet-Wittwig coupling, but other terms are not usual Maxwell term and Young-Mills. They have different actions. And I write equations of motion just to see that in general they're nonlinear and that they can have more solutions. But as I mentioned before, we took spherically symmetric ansatz because we wanted to study static solutions. And really, for us, it was important to choose a sector where we have where this ansatz gives like determined solution with well-defined initial conditions. So we take metric ansatz, most general spherically symmetric. We have metric function f, but also there is another function that can describe gravitational hair. And it turned out that even though a transversal section, say horizon, if we discover black hole, it can have different topologies. We chose spherical one because other ones, they didn't give so BPS state. So in general, we have 3 spheres at infinity at a spatial section. Now, because a transversal section is 3-dimensional, 3 dimensions have some special feature. First, I forgot to tell that for torsion field, when we take spherically symmetric ansatz, okay, there are different components, but we kept only 2 components that we found the most interesting, that in fact present 2 scalar fields that naturally appear. Okay, here they're in spherically symmetric ansatz, but in fact, one scalar field is the completely symmetric part of torsion that these 3 form effectively often appear in string theory. And the other scalar field comes from just symmetric trace, some of the torsion. So what is interesting also in 3 dimension, that torsion in the structure of indices looks very much like curvature. So the same as we can have constant curvature, we can have constant torsion maximally symmetric. So there is, in 3 dimension, there is like global torsion with maximal number of 3-dimensional supersymmetries, killing vectors. In that sense, we can, in other dimensions, it is not possible, but here we can also finally have a maximal torsion, maximally symmetric constant torsion. Okay, so now maybe I should have put that before, but I will just tell you why I will search for BPS states, for black holes that preserve supersymmetries. As I told, these dimensionally continued black holes that look like BTZ black holes, 3-dimensional black holes, in fact, they look in their energy spectrum very similar. When this mass parameter is positive, they define black holes in the sense that curvature has singularity. When mass is 0, then it is still with singularity, but this is the smallest black hole with 0 radius, also called like a ground state black hole. However, there is nothing to prevent mass to be also negative, and then there is singularity, but they're naked singularities without horizon. When m-1, then this is global anti-de Sitter space, and of course it can be even smaller, and again it gives naked singularity. So it was natural then to ask, if we introduce supersymmetry and find BPS state, will then minimum energy be here? We found BPS state, but we have not computed Bogomolny background yet, because anyway we had a lot of things to explore before arriving to Bogomolny background. So I cannot give you definite answer, but just probable answer that probably it will stop here. Without non-abelian fields, I mentioned already that they already found that there are black holes with constant this axially symmetric torsion. And also there are another black holes that Omar asked. I'm sorry, this is, no, I didn't write. In fact, this is what Omar asked. Here we have global anti-de Sitter space, for example. So there is no problem to have global anti-de Sitter space. If you add extra matter fields, then you can also have BPS states and everything is fine. Okay, and also there are many black holes, but I don't know if they're BPS states. So now the goal is to find a concrete BPS state black hole and to understand its properties, not only to find the solution. Okay, so now I will to focus to more relevant physical properties. I will just say that when we plug these ansatz in equations of motion, we find that there is one sector with this solution where everything is fully determined, but it gives 4 integration constants. What is interesting, it gives hair, gravitational hair, it gives scalar field that is in fact a torsion, but we can imagine this torsional scalar like scalar field coupled to gravity, where supersymmetry completely fixes its coupling. And also we have a gravitational hair that appear in just in the metric, and also this is a trace of the torsion. We introduce auxiliary function because later this function is related to behavior of anti-de Sitter field at infinity. That's why we introduced it originally. And if we see asymptotic behavior, it is quite reasonable. F tends to almost lost anti-de Sitter, but it is modified by gravitational hair. This hairy part tends to 1. The other scalar field tends to constant. Trace tends to 0, and AD, this is interesting that anti-de Sitter field tends to constant. It is not a 0. And later we will see that just to at once to know where we are, that mu will be related to mass parameter, C will be a charge related to axial torsion that will be related to amplitude of actual soliton, and there are 2 gravitational hairs that we will just decide to be 0. B0 we will choose B00, otherwise we will have singularity here in N on the horizon and we don't want it. And another here we will choose to have 0 only to have more standard behavior of the metric that is without gravitational hair. But honestly, this one we could have left. It would have been interesting to study because it would give this non-trivial scalar field solution. But like a first step, we chose all gravitational fields 0. In any case, with all constant, there is we can compute Hawking temperature. We can find that there are two horizons determined by mass parameter and this B gravitational hair. And when this is like in standard supergravity, when P is extremality parameter that describe distance between two horizons. So when horizons coincide, of course, then we have temperature 0 as always. And when P is negative, then we have naked singularities because horizon disappears. So everything here is more or less standard. Okay, so let's now focus to finding unbroken supersymmetries. In this particular case, I just repeated here solution, but then there is this parameter psi that become constant. I want to move a bit to physics, physical description. So what happened with non-abelian field? I didn't mention it much. First, non-abelian field equations of motion restricted to be defined only on the sphere, where theta are angles on the sphere. So now the form of this the field is determined by more or less by requirement to have a BPS state. And in order to have some clue what is its form, first we know that in order to have BPS state, we have to expect some non-trivial topological properties. So instead of just to do general story and to have a lot of equations as we initially tried, it is better to ask group theory to help us, and it shows us that in fact on 3 sphere, if we choose SU2 gauge group, then there is non-trivial homotopy group that is integer that just say that we could have maybe some non-trivial winding of non-abelian field SU2 around the sphere. This is, of course, just inspiration. If we find a SU2 solution, we have to check if there is really some non-trivial winding. But this was our inspiration. Why?
Sorry, Olivera, there
yes.
is a question by Cristobal.
Yes, Cristobal.
Cristobal.
Yeah, thank you,
Sorry.
Olivera. Do you have a torsional singularity in your previous solution? If I compute any torsional invariant, is there any singularity as well?
For the case that we take, we won't have, because our let me show the solution. This is our torsion, and we will take BZ. No, there is in R0 only, but there are no extra singularities.
Ah, okay. So it
just
is located
standard
at
ones.
I
yes.
see. Okay. It is located at the same point as the metric singularity.
Exactly. When we take B0 and metric, there just everything is regular.
I see. Thank you.
And I didn't write here, there is U1Q field that is 0. I didn't write it because at the beginning I told that it is not dynamical here, and it gives 0. Okay.
Thanks.
So, yes, I wrote it here. Okay, so here only in this sentence, only one scalar field survives. Okay, so now in order to find non-abelian field, we have to break the symmetry, and the maximal there. In fact, the group theory, we open some table of group theory, we find there are 2 non-trivial maximal subgroup to break it, but we choose this one, where in general we can have a like SU2, I will call them left, SU2 right group, and extra U1 charge. I call it now U1C because it is not any longer this initial one U1Q. It is just coming from internal symmetry. And even though this is one of our future possible works to find really solution of the whole maximal subgroup, but for us it was now sufficient to have at least one SU2 subgroup. In fact, it turned out that for static case, only one will give a solution, 2 not. We need the non-static case to have both SU2 groups. But it is interesting that this U1C field, for example, we finally give another kind of non-abelian charge for Dirac spinors. And also, finally, I will present here global sphere on the like topology. I will choose topology of the transversal sector to be global sphere. However, we can also, there is no reason not to choose some identification, where one of them is RP3, projective space, that is just quotient space of the sphere with antipodal points identified. But in the paper, we wanted to, we expected drastical differences between S3 and RP3, because it will turn out that we are in topological sector. In fact, it is not coincidence that we found non-trivial solution with topological numbers and that we are in topological sector of Transsignments supergravity. This was kind of finally to expect. I mean, we didn't expect, but it was natural conclusion. So we expected to have a drastical differences in behavior of the theory for different topologies, but even though some numbers are different, physically they're similar. I won't present here both cases, they're presented in the paper. Okay, so without passing to details how we compute solution, how we choose generators. Okay, this is finally we finish only the I hat means that we are in internal, that this is internal generator. So we have these internal generators. And finally, here, let me write solution for non-abelian field. There is only a component exactly defined on the sphere. That is some gauge field, in fact, that I call it, in fact, we call it just non-abelian soliton because it will have non-trivial topological number, I will show. But when I write later explicit form how it depends on angle, B can be understood like amplitude. Of course, this amplitude of the soliton that oscillates, maybe it is different in different directions, different angles, but finally it determines maximum somehow. And it is interesting that for general B, F is not pure gauge, but it tends to some constant value. And at first sight, it can worry us because gravitational soliton also has the same feature, I will write later. But at first sight, it can worry us because in Young-Mills theory, if field strength is not zero on the boundary, then we have infinite energy. And then we don't have soliton because with infinite energy, everything is possible. But here we will prove that energy is finite. I mean, it is not infinite at all. Okay, and we have also this U1C field that just becomes pure gauge. Okay, so B is new integration constant, but it will disappear when we require BPS states. But let me now summarize. In metric part, we have just black hole with the only parameter that is this mass parameter related to extremality parameter. And we have extra related to these scalar fields that come from gauge fields. We have two, I call them soliton, and I will prove later that they have topological charge, but let me now believe that they're solitons. One is internal soliton with amplitude B, and another is actual soliton with the amplitude C, and their field strengths on the boundary are constant and have this value. So, okay, so let's see if some class of this solution preserve some supersymmetries in bosonic sector. So we require, if we take fermions, because we look only bosonic solutions, if we take that fermions are zero, and if we ask if some supersymmetries keep this condition preserved, then we find that their BP, of course, there now, again, I eliminated one case. I eliminated pure gauge case that is also interesting. I don't, just need some water. I'm talking already 50 minutes. I will finish soon. Okay, no, 45 minutes I have been talking. Okay, so we also studied pure gauge solutions, and they're also interesting and even give more supersymmetries that are preserved. But I want to show on purpose this less usual case when we have a finite energy at infinity in spite of having a constant field strength. And then we find nicely, beautifully, that BPS states corresponds to extremal black hole when two horizons coincide. I mean, at first sight, of course, we know from standard supergravity this is true, but we are far from standard supergravity. So it was somehow reassuring knowing that this is also true here. But we also find nice that these two solitons have to have the same amplitude. In fact, we will see later that they become soliton and anti-soliton because there is some different sign when we compute topological number, and they unwind. That is also logical if you want to have balance of gravitational and internal forces, and in consequence, their field strength have to be the same. So this is kind of a pleasant surprise, and even explicitly finding the killing spinors, we find a solution that is some expression. It has a radial dependence fix. Here there is a phase factor defined by this U1 field, and there is constant spinor. This U1C field can give some phase factor. However, not general form of this spinor is a BPS state because we have some projection conditions that have to be satisfied that will in fact start cutting our supersymmetries and start reducing them. So first projection condition is that constant spinor has to be eigenstate of one gamma matrix that is associated to radial direction, and in fact it has to have a negative eigenvalues in our notation. If it is positive, then it does not give a good solution. So this cuts half of supersymmetries, but we find much more projection. This is enough that if we have pure gauge theory, and this is final result for the other solution that I didn't present here, that is 1/2 BPS state. But here is interesting that if we have also non-trivial field strain on the boundary of our solitons, that then there is this kind of twisting condition between internal generators acting on spinors, because each spinor has internal index and the spinor index. They're charged by internal symmetry. So internal generator acting on spinor has to be equal to external gravitational generator, anti-de Sitter generator acting on spinor. So this is many equation, in fact. So it can be so strong condition that it cuts all supersymmetries and there is no BPS state. But when carefully done, we even chose particular representation just to be sure. And we found the explicit form of this spinor. It turned out that there are just 3 conditions. So we already had 2. So in total, we had 116 BPS state. So we have reduced supersymmetry, but still we have, I think, at least 16 supercharges. So it is still fine, and we have 1 supersymmetry. Of course, there is this other one with just 1/2 BPS state. But this was first conclusion that is nice. We have a BPS state. Okay. There also we check they're globally well defined. They can be periodic or anti-periodic, depending how holonomies cancel with signs plus or minus, so everything, this is also important. Otherwise, if a spinor is not globally well defined, it has to be eliminated. But what are now topological properties of this spinor? First, there are different topological conserved current that we could define, and we check few of them, and they give 0 charges. But there is one that is in fact Pontryagin topological invariant, but only in a static sector. So whose boundary is 3-sphere. So if we now look, and of course, this current defines conserved charge that is topological charge, because it is not based on symmetry. So now, just looking how many subgroups we have, and we know that SU2 is a candidate to give non-trivial number, and in fact, it will give non-trivial. So we can define, in fact, many topological charges, but they are not all independent. For example, we can wind this defined Pontryagin index only for internal symmetry, or only for SU2 subgroup of anti-de Sitter, or for total, or for the whole, if we want, even for the whole SU2 to 4 group. But in that case, there is no, it is not integer, because there is no non-trivial winding. But of course, I'm just now showing them, and interestingly, we will see that these charges that we discovered here, in fact, will appear naturally like conserved netter charges that come from U1 Q field that is topological. So even if we didn't discover this Pontryagin number, it would have appeared naturally as netter charge. But what is new in topology is that there are some quantities that will be quantized, because this value has to be integer when properly normalized. Otherwise, topology does not allow it to be anything else. So this is also important and new. To compute all of that, just for your intuition, we took, this is just to see what I told, that B is really amplitude. We chose particular coordinates that are Hopf coordinates just by chance, because Hopf coordinates have some interesting feature that finally we didn't use, but maybe we will use in future. But in any case, in Hopf coordinates, you can see that B is just amplitude depending on direction. And so I wrote here only internal soliton, and absolutely the same form has ADS soliton. Okay, so plugging in the action, not in the action, in Pontryagin invariance, we find that, for example, these amplitudes cannot have any form, that this soliton exists only if B is such and C are such that these are integers, you see. So this is interesting. So solitons are not completely arbitrary, they're kind of fixed. So we already see that we cannot vary them somehow, because there are no variations of this expression if it has to be integer. Why I say that? Because later I have to compute charges and I use Hamiltonian formalism. But I just want to point out that we find that 2 solitons have quantized amplitude by topological numbers. However, total Pontryagin is not quantized, and it is consistent when we compute it, it appears mass parameter. So this is also nice. Mass is not quantized as in standard gravity, where all other charges, for example, Reissner-Nordstrom next black hole, it has electric charge, has somehow topological origin in a central charge of the algebra, but mass remain continuous, and also charge is quantized. But here we have something similar, that mass will remain continuous, because homotopy group tell us that P is not quantized, but solitons have quantized amplitudes. Okay, now also beautiful solution, beautiful conclusion is that we now require BPS state, and we find that in this case, the total topological number has to be 0. That is logic, because soliton and anti-soliton have to be in equilibrium if we want for them to be stable. So this is also, and BPS state is, a black hole is extremal. So this is also kind of a nice and unexpected thinking that we are working in Transsignment supergravity. And this is, I already told you. My alarm is telling me that there are 5 minutes, but I have many transparencies just with conclusions. So we are fine with time. I just want to tell you, without writing formulas, particular problem was how to define the charge. Because as I told at the beginning, many formulas are based on the fact that we choose asymptotic background, that is anti-de Sitter in this case, and it is linearized around this background. But here we cannot linearize because ADS background is twofold degenerate. So if we take some ready formula for asymptotically anti-de Sitter spaces, we will find unpleasant surprise that it fails, it gives all 0, and that it is not well defined. So we cannot use anything that linearizes. On the other hand, there are also many people here have been working in Transsignments, anti-de Sitter gravity, for example, even with or without torsion, but there are netter charges, for example, without torsion. In this paper of Olea, Troncoso, Zanelli, Pablo Mora. However, they work with also with without torsion and asymptotical anti-de Sitter space, and we cannot apply it directly, it does not work. We should define our own netter charge. Or we can, trying to avoid defining our own charge, we can try to use Wald formula, but Wald formula is not applicable when we have torsion, only when we have curvature. So we cannot apply either. And it is just for gravitational part. Of course, we can just evaluate out. Okay, this is if we have charge. Okay, so we decided to use Hamiltonian charges that does not have any of these restrictions. And in fact, it is known that But the problem of Hamiltonian charge is that only variation of the charge is fixed by differentiability of constraint in Dirac method, but it is not guaranteed that it can always be integrable. And what is interesting, and also parameters are not any, but they have to be covariantly asymptotically constants and variations fixed on the boundary. So we have to solve these conditions, and we find that only abelian charges from non-abelian part, from internal symmetry part, we can have only non-U1 charges, not non-abelian. And from a gravitational part, we find one charge that it turned out also logically that it exactly corresponds to time-like killing vector. So these two nicely coincide because we were worried that they won't coincide. But still there is a problem. They're metric and even parameter, and many things are linear in R, so they can give divergent energy. So we were also worried about that. But when we and whether this is integrable. However, if we choose that amplitude of the soliton, gravitational soliton does not vary, that now we understand why it is logic, because it is quantized, it cannot vary. But then if we take the variation is 0, then it is even integrable. We can even solve everything perfectly. So now I'm free to give you result, and it is in fact a very consistent result. It gives us black hole mass that is standard expression. We were checking without torsion, for example. This is typical expression from black hole mass of twofold degenerate vacuum that is obtained even using different methods from a thermodynamic point of view. And in fact, in torsionless limit, it gives even vacuum energy of anti-de Sitter space, and all coefficients and everything matches perfectly. Also, we find that there is some interaction between black hole and this soliton that is not surprising. But now there is soliton energy, and because our soliton is fixed, I would rather interpret it like soliton vacuum than, but this is soliton energy, soliton vacuum energy that is in this solution. So as you can see, all divergences cancel out and we have finite energy. Fine, there are also some abelian charges, and you can see again, funnily, they just depend, B and C are function of M. So they're just topological charges. This is what I told you at the beginning. Our topological U1 charge, in fact, is U1 Q charge that does not have locally dynamics, in fact, is topological charge. So this is super consistent with this formula. So finally, in spite of everything, we have quite consistent results. And I already told you all similarities with standard supergravity. So I would jump these slides because I already told you during my talk. I would like only to say, even I will jump additional results, and honestly, there are many, and we found some other solutions, non-trivial, but I would like only this blue text to emphasize. We took quite difficult task to calculate, fine, what is the number of degrees of freedom in this theory that we chose, because I told you that different sector has different number of degrees of freedom, and we were super pleasantly surprised that is in fact logical now when we look that there are no propagating degrees of freedom in the book. That is logical. We have just two solitons, and this black hole in fact is very similar to BTZ black hole, but here we see that it is topological, so it is also nice. However, there are many open questions. First, topological invariant that we look was Pontryagin, but it is more interesting to see like the full topological invariant 5-dimensional. But for that, we need non-static solution, and we need the full like SU soliton that has left and right side. And this would, we're interested in this because this would look like Young-Mills, because then we could have like anti-self dual soliton. We already were playing a bit with this, and we got something that looked like, you can see the paper that look like this in static case. But finding full soliton, it would be interesting because it would again mimic Young-Mills and show that it is not coincidence and not particularity of Young-Mills or supergravity, but these are more universal features. And of course, we have to compute charge algebra, central charge, and to find that energy is really bound from below loop, starting from typical supersymmetric properties of any algebra. Of course, we computed black hole entropy, that now when we have charge, we can evaluate it on the horizon and compute entropy, and it gives some expression. But before checking all black hole thermodynamics, that was already too much, but it is absolutely necessary also to see that. So thank you a lot for that. And this work was financed and supported by different grants. So
thank you very much, Olivera, for this fascinating talk. Are there questions? I see that there are already at least two. Okay, so please go on. You can switch on your mic and ask. Okay.
So I have a short question. Like, have you considered pure Lovelock in 5-dimensional theory?
No, because pure Lovelock does not have double degenerate vacuum. It does not have. It has in fact unique vacuum.
Mm-hmm. So that's you found the argument that it won't work or it won't be interesting.
No, In fact, pure lovelock is completely different than this class of theories. The idea here was to start from Einstein-Hilbert plus Gauss-Bonnet, and by chance to finish in supergravity. And of course, there is because then we know how to supersymmetrize. But of course, about pure lovelock, you have, if you want BPS states, you have to supersymmetrize it first.
And you haven't found the supersymmetrization done?
Yes, for Gauss-Bonnet, there is super Gauss-Bonnet.
But for pure lovelock, we don't have it. Yeah, we wanted to do it in the past, but
yes,
we gave away. Okay, yeah. So thanks for the answer.
Okay, are there more questions?
I've got lots, so maybe I should leave it for the discussion session. So that'll be okay.
Okay, yeah, perfect. It would be
better.
Okay, so I would say that we can end up here the talk part of this workshop. I would like to thank all the speakers and all the audience for sticking with us. So now we will have 13 minutes of a break. So we will meet here at 5:35 Central European Time for the discussion session, which will not be recorded, so you can ask all the questions you want to the speakers.
Forbidden. Okay?